Hello everybody. I'd like to welcome you to our first webinar of the season with our own Valentina Prado talking about Anticipatory LCA 101. Valentina brings extensive expertise in developing decision analysis tools for life cycle assessments, LCA, and hands-on experience in the Sustainable Return on Investment, or SROI, assessment methodology. Her research focus has been in the incorporation of decision analysis to the interpretation stages of comparative LCAs and tackles issues of normalization, weighting, and uncertainty. Prior to joining EarthShift Global, Valentina was an assistant professor at the Institute of Environmental Sciences at Leiden University in the Netherlands, where she taught LCA theory and application in the master's program of industrial ecology. She also supervised master's students in their thesis works. She's conducted several SRI workshops for EarthShift Global's predecessor company and has done groundbreaking work in decision support for LCA, which we will continue to extend as part of EarthShift Global's suite of tools. So without further ado, I'd like to welcome Valentina.
Thank you, Holly, and thank you everyone for joining this webinar. So the aim of this webinar is to introduce the concepts behind anticipatory LCA. Maybe I think many of you in the audience have heard about anticipatory LCA, ex-ante LCA, prospective LCA, LCA of emerging technologies. There is this great push to apply LCA early in the development phases of a product or a technology. So while we let's say we as, this audience, this virtual audience, well, we may be versed in LCA, we haven't applied this anticipatory LCA approach yet. So this is aimed for those that know LCA and are interested in how they can use LCA to guide technology and product development. I will be focusing in anticipatory LCA. There are some, let's say, nuances or differences between prospective and ex-ante LCA, but I think in general the underlying motivation is shared between these different approaches. So if we start with technology development, we know that this is moving really fast. This is moving faster than how we can capture the environmental impacts of these technologies that we're developing. And in fact, many of these technology development is environmentally motivated, right? Let's think of renewable energy, energy storage, biomaterials, right? There is all these development of technology material that is environmentally motivated, but most of the time this development is based on a single property. So we are doing all efforts to make solar panels more efficient. We see an increase of nano-enabled technology in solar energy or even battery storage. It's all about this efficiency, and that's great. I mean, it is a huge part of making these technologies competitive. But as LCA practitioners, we know that that single property does not ensure, is not a guarantee that environmentally would be better, right? So I'm just showing you examples, studies out there that are, pushing for these new technologies and new materials, and many of them are environmentally motivated. So bioplastics, right, the promise of plastic from plants, or glucose, or shrimp shells, right? These all seem great ideas, but just because it's made out of a plant or a shrimp shell, we know that that may not be enough, that we need to look at the whole life cycle. Right? We are LCA practitioners. The whole point of LCA, we know, is to avoid burden shifting. So we need to take into account all of the stages of production, raw material extraction, production of a technology. showing you this diagram, which I know you have seen many, many times. So you could probably close your eyes and just have this diagram already, you know this by heart. But let's say one of the challenges of applying life cycle assessment for these new technologies, which are already which many have an environmental motivation, underlying environmental motivation, is that if we look at the stages of LCA, so goal and scope, right? If we're looking at developing a new material that may have many applications, we may not know what the scope is. We may not have an exact functional unit in place because this material with these properties that we're developing may be used in batteries or certain electronics or, I don't know, lightweight materials, right? So if we don't know what the functional unit is, it's really difficult to define the scope and, of course, the goal. So that's a challenge for these technologies that are really early on in the development. The other part is inventory analysis. This is the data that we collect that as LCA practitioners, we know that this is tedious work, this is burdensome work. And imagine doing this for a technology that is not at a fully commercial scale yet, that we're still tinkering with it at the lab scale, and it's going to change every experiment that we do. So that's a challenge. The third part is the impact assessment. Usually as LCA practitioners, we don't deal with this part very much, right? We don't characterization factors. But when it comes to these publications, and they have different versions of this graph, but here I've just made it the most simple of all. I've tried. So in the x-axis, we have the stage of technology development. We have from really early at the lab scale, we're just making one cell, 1 gram of the material, to fully, so it develops to a fully mature technology. Think of car manufacturing, for example. We have been doing that for years. We know how that works. In the y-axis, we have the degrees of freedom in the design. How many components of this product or this technology you are able to change. How many different configurations are you able to play with, right? This space is much greater at the beginning, where you're still tinkering and you're playing with the design. However, also in these early stages where you can play the most and you can explore the most configurations, you also have more uncertainty because it's early on and things are not defined yet. If we think about applying LCA, so we have this great uncertainty. The more mature the technology is, the less uncertainty we have. The more data we are able to collect, the more we know about how this technology is going to perform, how this product is going to be used. It is much more convenient for LCA, right? We have less uncertainty, we have more information. However, the degrees of freedom is also lower. This means that let's say, when you do an LCA and you identify hotspots, what you can do with that information is limited because so many other things in the supply chain, in the product composition has been set, right? So is this challenge, this dilemma? We can do it earlier on where it's most useful, but it's most difficult, or we wait until later on. And yes, I mean, there's been plenty of success stories of how products have been developed and have improved, but it is limited. It is, we're talking about, more marginal changes. Ideally, you would have this environmental insight parallel to the product development. If we are aware that we need to include the whole life cycle of a product, why wait until the end? Why wait until everything has been figured out and then we do the diagnosis of the environmental profile? So the motivation of this anticipatory LCA is to try and use LCA, the LCA framework, to explore how this technology, how this product may perform, but do it early on. So I'm going to go over and show you examples of studies that have applied anticipatory LCA with the aim of give you some ideas. And I want you, if you're working at a company, if you're working at an organization, working in product development, either at a lab or at a commercial scale, I want you to think of how you may incorporate some of these tools, incorporate some of these ideas into your own organization. How could we make LCA a more proactive tool? So this is the Anticipatory LCA framework. This is how it was published for the first time. It was a featured article in Environmental Science and Technology. You can read more about this article, and I've left the name here on the bottom right corner. But I'm gonna just reduce it so it's easier to your sight. So the Anticipatory LCA has this. I'm going to divide it in 4 components. We have the technology model, which is the inventory. This is your unit processes, right? Information about manufacturing, raw material, information about how this product is going to perform in the use phase. We have the impact assessment, which, as I said, as LCA practitioners, we usually don't deal with this directly, but this is about characterization factors. On the left, with the little heart, we have the social context. This is the functional unit, the boundaries, the weight, which is the stakeholder preferences, the impact categories. What are we going to evaluate about this product or this technology? These components together give you the LCA results, right? But we know that LCA results can be difficult to interpret, particularly in comparative cases. Right? You're comparing this new technology with something that already exists, and you include multiple impact categories. Often there is not one single best alternative. So how do you deal with these pros and cons? How do you deal with uncertainty? How do you deal with conflicting stakeholder values? Right? So in the Anticipatory LCA framework, there is a decision analysis platform, and I will cover this in a little bit more depth, but I will focus actually in the inventory part. So from these results, we rank these alternatives, and you would say, okay, this out of these 5 different, let's say, configurations of the product, these 2 configurations have the most environmental promise. This one, definitely not. So that's information that you get from a ranking. We can apply a global sensitivity analysis to that, and so we can provide feedback. Okay, if we are going to refine this study, what do we need? Do we need better characterization factors? Do we need to go back to the lab and do more experiments with zebrafish? Do we need to refine or look more into these technology parameters, to the manufacturing, into the use phase performance? Or do we need to have more information about the preferences of stakeholders? Or does it really depend on the functional unit? And that could relate to how the product or the technology performs. I've skipped over something important that I want to say about this approach, and it's these 3 words. Anticipate, so try to maybe not look at this really complex diagram that looks like a bowl of spaghetti, but let's look at these 3 words, right? So Anticipatory LCA is explorative. We don't know how these technologies, how these products are going to perform once they scale up, once they are in commercial scale, right? So something that is important to note here is that Anticipatory LCA is not trying to predict. This is not a prediction tool. We are going to explore, and to explore with the aim of aiding in the design of the technology. What is the technology that we want? How does it look like? Under what circumstances is this technology, is this product competitive? Right? So we are exploring different conditions. And in this manner, let's say we release ourselves from trying to, predicting is hard. And there are so many parameters, so many variables that you can go into a prediction exercise. But I think that for guiding the design of a technology, the exploration is more useful. So explore. design. And the third keyword of anticipatory LCA, I would say that is comparative. If we're developing a new solar technology, it needs to be competitive with at least the current alternative. How does it perform? How, okay, maybe it's in the lab scale and manufacturing is really, really intensive. Well, how much does manufacturing need to improve? By a factor of 2, 100, 1,000? If this technology, let's say, reaches the thermodynamic limit, so perfect, let's say, performance, how does it compare to the existing alternative? So having that reference point, that baseline, allows us to, see where this technology or this product needs to improve the most. Otherwise, we would keep developing a product, developing a technology, and then where we have less flexibility with the design, that's when we're trying to make the changes. So that's when I say we want to make or anticipatory LCA is about making LCA more proactive rather than a responsive approach. So the technology model. Going with the keyword of exploration, right? So if you're dealing with a product or a technology, and I use these two interchangeably, so if I don't say both, you can assume it's both of those things. But if it's in an early stage, we know that if we compare it to the existing competing alternative or something similar, because some products don't have a competing alternative, but a reference point, right? Well, the manufacturing and the supply chain is not set yet, so it's not going to look well. It's not that comparison of something that is in early stages of development and a technology that is fully matured is not a fair comparison, right? So we need to kind of explore how this technology, how the product development is going to scale up, how it may develop or how it could develop. So I'm putting these different efforts into what I'm calling process improvements. And there's different ways you could explore how the processing of a product or a technology could improve. And this is not set in stone. This is my interpretation of the literature and from my knowledge. So 3 common things that I see is experience curves and thermodynamic limits, how, let's say, similar technology or the same technology has been evolving, has been progressing over time, right? So for example, I'll show the example later on. The second one is economies of scale. We get better at producing things the more quantity we make, right? So there are different, let's say, technology parameters that would improve if we look at scaling up. The third one is operating conditions. This could be the energy that is utilized or just changes in the operation that would reduce energy, that would increase efficiency, that would improve yields. In the end, we're looking at the bounds of this product and under what circumstances, under what conditions would this product be a competitive alternative. These bounds or these conditions give us a design target, right? It is like a map, right? It tells us we need, if this technology is going to be competitive, we need to look, okay, I think we've got with the efficiency, we really need to reduce the manufacturing impacts. That's where we have the most potential for improvement. If we don't improve the manufacturing efficiency, the manufacturing impacts, we may keep reducing the weight of this product. I don't know, I'm just saying examples, but that's not where the big improvements are in terms of environmental impact. So it may be that, we're not predicting, we're not saying this technology is going to be produced this way. Sorry, I have a comment. Okay. It's not going to be produced this way, but that's where we need to go. That is the technology that we need. That's what we want if we're looking at something that is environmentally advantageous. So I'm going to show you some examples that I found that are in the literature. Let me move. I think this is blocking the view. Okay. So experience curves. This graph here shows for single junction monocrystalline PV devices. So this is a specific line of a specific type of PV panels, solar panels. And in the x-axis we have the years, right? So we see how the efficiency of the new models have increased. We're making more efficient modules each time. And in blue, we see the range of the the embodied energy. You think of, the manufacturing, the energy that it takes to produce a watt of this technology. In 1998, well, the range was really wide, but we can see that overall the manufacturing, the embodied energy has reduced and the efficiency has gone up. So we're making more efficient panels with less energy. If, let's say, we are looking at, and the third line here, this is the limit. For this technology, basically, the highest efficiency it can reach is 29.5. Again, for single junction monocrystalline PV. So if, let's say, we are developing the new generation of single junction monocrystalline PV devices, we could look at this trend and say, okay, in 15 years, we're going to be, I don't know, at 20. We're going to be at 20 and our manufacturing energy is going to be here, right? So, but the point is that this gives us an idea, a starting point of conditions to explore. You can look at also similar technologies, seeing how we have improved over the years to give an idea of what could be a possible improvement. More examples. This one relates more to economies of scale. So what some studies, anticipatory LCA studies do is, as I said, they because of increased increments in scale, certain technology parameters improve. This is the case of a water filtration technology, and I want to point out to this thing in the paper that says to demonstrate how each sorbent for water filtration can be improved to outperform the existing technology. An improved scenario was also evaluated. So they're calling it scenario, and that's fine. You can call it a scenario as well. But what they mean with this improved is that they look at the performance, how the energy that it takes to go through the filter, how well it cleans the water, how the manufacturing energy of this filter. So they are changing. The point is that they change more than one performance parameter, and they're calling it an improved scenario. You can call it a best case or an optimum case, and you can have multiple of those. You can have like a progression. And in fact, this progression, some studies categorize as lab. So lab, pilot, and industrial scale. At the lab scale is basically the inventory that you would have now, something that you are, the material scientists or your engineers are still tinkering with. This is at the lab scale in a clean room, right? If we say, okay, this is not going to be in a clean room anymore, this is going to be, the pilot scale, some improved parameters, and this would be a pilot scale. And it improves even more, and we're going to call this an industrial scale. That's also another approach that you can use. The idea is, explore different conditions, identify, what are the optimum circumstances for the product that you're developing or for the technology. This one, I think, was an interesting study because it looks at it bases. So all of these are process improvements, right? And these are just different ways that researchers are deriving those improvements from. So one idea also is to look at similar industries. This study is looking at laboratory meat. So for those foodies that are always trying to look at the latest food, so I think this is really the latest technology. So I don't know, I like this figure of the paper. They looked at land use, industrial energy use, and global warming impacts. So the in vitro meat that they studied plots here, which means way less land use than beef, but more industrial energy use and less global warming. But they look at they made a combination of the laboratory data and they scale some of the manufacturing, or sorry, the processing based on pharmaceutical and beer industries. So the building energy use and other parameters in their technology model, they are basing it on other industries. And you can, I think these slides will be available, so you can look also at the study and see how they do that. And here I'm highlighting another example for so for example, the baseline facility energy required for lighting, HVAC, and other purposes was assumed to be equivalent to a warehouse. So they're borrowing information from other industries. This in vitro meat is not being produced at the scale that they are evaluating it, but they're using, right? So as a proxy. And as LCA practitioners, we use proxies all the time. So this is something that I think as an LCA practitioner you could be comfortable with. Of course, we know that these results are explorative. They're not predicting that in vitro meat is better, but they're looking at, evaluating the potential of it. Here's, I think this is the last example for the technology model. And this one is in fact co-authored by Lisa Lauren and Nathan Ayer from EarthShift Global. This is one of the studies that we supported. But what I want to highlight here is that this study, they looked at future scenario assumptions. So you can, could be an improved scenario, but they are changing different technology parameters. So they're saying with an increase in scale, instead of this mixer, we have this other mixer, so there is a reduction in energy. There is a reduction in centrifugation because there's going to be this other module attached to it. We are betting on higher oil extraction, and it's going to be fueled by a low carbon energy, right? So combining these different parameters, you can also call it some sort of sensitivity analysis as well, but you're exploring, again, these improved conditions. So that was the technology model. Hopefully gives you ideas of how you can use this in your own organization. For the impact assessment, I'm going to go over this more briefly. We have basically there are different research efforts here, and really all looks into stochastic characterization factors. And what this means is that, how characterization factors is just, one number. We're looking at a range of values because, well, there is uncertainty. One of the efforts in this direction, and it can be applied really to any characterization factor. So you could think about this in a generic way. This example that I'm showing here uses U-stocks, but just like U-stocks in any other characterization factor, there is an underlying model. There's an underlying model that describes the properties of the media where the chemical, the substance is released into, properties of the substance itself, how much does it dissolve, how much does it attach to fat or water, how much of it do you need to kill 50% of the zebrafish population that you test. This is not really my area of expertise, but I know the underlying concept. So this is, you know, as I said, just the main concept of it, not a detailed account of it. But in any case, so you have this model with these different parameters looking, you know, that describe the conditions of the media and the chemical, looking at toxicity because this is a toxicity model. And here you see, for example, for each one of these, so this is the coefficient of partitioning, you can assume a uniform distribution. So this is a range, a minimum and a max, or if you have more information about it, of a chemical that doesn't have a characterization factor yet, you can apply other distributions. This minimum and max could come from, maybe there is no actual study that looks at the KLW of this chemical. Or maybe there are, but they're differing, right? So there is a range. Some studies say this, some studies say that. So you may include that range. Or you would say this chemical behaves like this other chemical and that other chemical. So you would have, again, you know, that range. The idea is to explore the range of each of these parameters so that together you get a characterization factor that covers that uncertainty. So this is an example. You can see more about this approach in this study that was just published last year in the International Journal of LCA. This is an example of an illustration of the characterization factor that was developed this way. And then you could see, you know, this range. Attached to this, there is a possibility to apply a Spearman rank correlation index, which basically looks at the underlying parameters and evaluates, if I want to reduce the uncertainty of this distribution, which parameter do I need to, which uncertainty do I need to reduce the most? And in this case would be the coefficient of degradation in water, I believe that one is, and the toxicity parameter, the EC50. The idea is that we throw these possibilities into the model. We have a range, but then we can refine it. It's better than trying and, you know, investing resources in polishing and refining all of these parameters, right? So this is also a way to save resources, to be more efficient with the time and resources. But as LCA practitioners, you're not typically going to deal with this part. This is something that you would either use existing methods or work together with method developers. The other part of anticipatory LCA is the social context. So it includes multiple things, right? I mentioned the functional unit, in which case I would suggest that you test multiple functional units. But one of the particular things that I would want to focus in for this is the weights. Usually when we are developing these technologies, you know, there's a focus on a single thing. And even if we include the whole life cycle, even if we manage to include the whole life cycle considerations, we may still be focused on a single indicator, right? Like climate change, just looking at climate change or just looking at energy. But in reality is that there are, you know, multiple dimensions of environmental sustainability. So a way to include this in the assessment is by, that is done in Anticipatory LCA with the decision platform, is looking at stochastic weights. So when we look at impact categories, we may be looking at about a dozen impact categories, or 8 or 12, right? So each one of these represents a dimension. Here in the slide, I'm including 3 because it's the amount that I can graph in this two-dimensional space that is the PowerPoint slide, right? So you could think about global warming, is one dimension, one impact category that you would consider. Dead fish, or I think this is, I don't know, you could, ecotoxicity, and human toxicity, right? It could be any 3. And these together, think of, a surface. When you include 8 categories or 12, well, this is going to be more complex. But if we look at these 3, together they form a weight space. If we know nothing about weights, which is often the case, we don't know what the preferences are. We know, however, that weight values range between 0 and 100, or a 1, depends how you scale it, but that have that range, the minimum and the maximum, and that when you add the weights together, they should add to that maximum, either if it sets at 1 or 100. With this information, we know what this space is, and we can assign distributions, the same distribution to each one of these, so that we sample all the possibilities within those constraints. And you would get something like this in the bottom. So in the example in the bottom, there's 5 categories. And what you see is 5 distributions overlapping, right? Because it's the same distribution for all of them. So this way, you're sampling the same weights for all of them, but you're taking into account that range. You're considering that global warming may range from being really important to having really little importance at all. You're giving the same opportunity to all of these different views. One alternative, or how this is usually done in LCA, is looking at equal weights, right? So it would be 33, 33, and 33. But what does this 33 mean? If we think of, let's say, controversial topics in our society, things that are polarized, right? We have people with opinions in one end and other people in the other end. If you take the average, you represent no one. If you take one side, maybe you represent 50% of the people. But if you take the middle, you represent no one equally. So the idea is that by using this stochastic approach, we can cover that spectrum of value systems or of opinions. Of course, if you think of this area, we can cut it, we can modify it, we can make constraints so that you represent priorities. You can represent a stakeholder that has a priority that prioritizes global warming, or that prioritizes any of the other categories. But the default is all-inclusive, all possible weights, without giving, let's say, higher weight values to any of them. So it's a different approach to weights. And these weights would go into the ranking, which I'll show in the next slide. So the interpretation is composed of multi-criteria decision analysis, which is a huge field with, 100 methods, right? But we use a specific one, and sensitivity analysis for feedback. So this is what they're ranking. We use SMA, stochastic multi-attribute analysis. You can read more about it in the publications below, and in this presentation, I'm just going to show you what it looks like, what it does, but I'm going to leave the explanation of this for another time. So SMA allows you to rank the different alternatives, provided uncertainty, provided the different weights, and provided that you have conflicting results. So that, for example, cattail, this is an example of different PV technologies. So cattail, amorphous silicon, single silicon, and there's other ones here that I'm not labeling. Oh, here they are, multi-silicon, ribbon silicon. In this case, when we did the LCA, the comparative LCA of these PV technologies, there was not one single technology. And let's think about it in generic terms. There was not a single alternative that was better than the rest in every single impact category. So with SMA can, let's say, is a way of aggregating these results into and provides a ranking because it takes into account the uncertainty. Your ranking is probabilistic. So we're used to seeing a ranking as, you know, the first, the second, and the third. But in this case, we have, for example, in the first place is cattail is 60% likely to be first, and amorphous silicon is 40% likely to be first. So the first place is actually quite competitive between these two alternatives. In the last place, we have single silicon that is the most likely to be last. And if I remember correctly, this was because actually single silicon was had the highest efficiency, but also had greater manufacturing impacts. So if we want to refine this, you know, if we say, I don't know which one to pick, or I don't know which way to go. And I can refine this study to discern these alternatives. I could apply a global sensitivity analysis, and in our last publication last year, we show how to use this global sensitivity analysis especially to evaluate this type of ranking. So we would see we would need more information or more refined information about the agricultural land occupation of cattail, right? So if we can reduce the uncertainty in this impact category for cattail, we would be able to discern these alternatives a little bit more so we can make a better decision. Okay. Yeah, it's 148. Okay. So some final thoughts. Anticipatory LCA can be useful in incorporating environmental thinking from the beginning, even though, let's say, these products or technology, as I said, are environmentally motivated, right? Just because it's solar energy or just because it's bio-based doesn't mean that it's environmental. It is, and I mean, it's fine that is like that. It's a part of it, but it's not all of it. By environmental thinking, I'm referring to, you know, let's think of where these materials are coming from. How is this technology going to be disposed of or recycled at the end of life, right? So often, you know, the material development is so focused on the use phase that it is really difficult to deal with that material at the end of life. Could we do everything? Could we do a material that is high performing and yet recyclable, for example? So anticipatory LCA, or just, you know, LCA thinking early on ensures that systems thinking. And then the other parties, you know, explore, think of how this product, how this technology may perform. What are some of the process improvements that you could think of? Let's identify those conditions. So now I want you to think of how you could use these concepts to overcome the limitations in typical LCA for early product development. And think of using LCA more proactively in your organization. We're going to follow with some examples of how industry is applying these concepts that, you know, we hope to give you an inspiration and further ideas of how to do this. So our next webinar follows with Anticipatory LCA in industry. Lisa Lauren is going to cover, I believe, two industry examples. At this time, I'd like to thank you for your time. Thank you for your interest, and I welcome questions. Thank you. I think the questions from Holly. Right?
Hello, yes. Thank you so
Hi,
much,
Holly.
Valentina. I do have a number of questions for you from people here.
Wonderful.
The first is, could you please speak more about how the boundaries of an LCA affect their results, and how can you overcome doubt associated with LCA results due to this?
Thank you, Holly. That's a good question. I would say sensitivity analysis. Yeah, sensitivity analysis is a way that you could, that you can overcome these doubts. So one of the ways that these boundaries would affect your comparative assessment would be allocation. So what do you do with co-products, or how you account for recycled inputs? We know that is one of the main factors of what can flip results, change results actually, but then with a sensitivity analysis you could see whether the change in results would flip the outcome of the study, right? So if you're making a comparison and you have, let's say, multiple ways of allocating, well, maybe I apply, the 3 different ways or 4 different ways of allocation, but I'm still getting that, product A performs better than product B. Yeah, so that would be a recommendation. Thank you.
Okay, another question. Do you have to apply the entire approach to create a robust anticipatory study?
I like these questions. No, I don't think so. And this is why I focus more on the technology model part, because I think making this step is a huge step. It's already an advancement. Of course, I'm giving you these, if you see, for example, this decision analysis and these feedback approaches, their publication date is 2017, 2018. So, we know that the industry practice follows the advancements in academia. So no, I don't think so. I think there is a lot of merit and a lot of insight that you can get from applying it, and just looking at the process improvements, doing some comparison. As you do this more and more, I think you would advance your practice, but step by step, I think that's the way to go. Yeah.
Okay, thank you. If LCA were performed too soon or at a development stage with high uncertainty and its results were heeded, there'd be a risk of wrongly derailing a new technology through misanticipating its impacts. Can you comment on the right point at which to perform anticipatory LCA and or recognize when the uncertainties are too high to support robust LCA conclusions?
That is a good point. And what do we mean by, by derailing or having an assessment? I see it, if we don't do an assessment at all, then that's, what are we basing this technology on, or this development on nothing? And I think that's more uncertain. And as I said, Anticipatory LCA is not trying to predict how this technology is going to perform, but is looking at changing different parameters and seeing which parameters make a difference.
Mm-hmm.
But it's really, I think it's a hard question, and I don't think there is a point where you would say this is the right point. And even the analysis can take a different shape early on. Early on, you may just take a list of categories, a list of environmental impacts, and think of how this may affect these different environmental impacts or contribute to these different environmental impacts. Think of how would the supply chain look like? How would this technology, how would we deal with this product at the end of life? Are these materials that we're putting into, how recyclable are they? So it could be just asking questions about the life cycle and not necessarily jumping into an analysis right away.
Okay.
I think that could make sense, yeah.
Okay.
Then maybe putting numbers when there is so much uncertainty, yeah.
Okay. Valentina, when comparing a new technology under development with an existing mature technology, it is likely that existing technology also improves. And how would you account for this in the assessment?
Thank you, Holly. In fact, other researchers have pointed out to this issue, right? So we are comparing to something existing. We're assuming basically that the current technology is not advancing and that, this technology that it's in the lab scale is going to improve. But hey, in 15 years where this is going to be commercial scale, this one is going to improve too, right? So that is something to take into account. But if we could learn anything from that, is that then really this new technology must then perform, not just competitive to the current alternative, but actually have a bigger margin because we know that the current technology is going to improve. Or, it depends on the resources that we have for a study. There's different, as I said, extents of how you can apply this. And, it's an approach, it's not a specific method. So it could be, okay, we know that there needs to be some sort of margin, or if we have more time for the analysis, hey, let's do some process improvement in the current technology as well. But if anything, it tells us, it just makes it, let's say the target. We know that the target, it could be underestimated because the current technology will also improve.
Okay, I think we have time for one more question. Could you elaborate on the stochastic weights? Could these be considered neutral?
Thank you, Holly. So the stochastic weights, I'm going to show them on the screen. These are the stochastic weights. And so what is neutral? And I think that when it comes to value systems, and these are opinions, these are subjective feelings, right? When it comes to that, something neutral is something that is inclusive of all of us. If I take all of our opinions and I make an average, that's not neutral. That is actually, that average represents a really specific point of view. And that's in fact what we are doing with weight in LCA currently. We either take, all equal, or we just take one specific value, or we make a survey and we make an average of that survey. These are the weights for Japan, these are the weights for Australia. But in the end, those weights, right, come down to a specific number. So I think that this all-inclusive approach is more neutral because it's giving a space to different types of opinions, different value systems. By including this, we are including in our analysis, in our results, let's say instances where global warming, as I said, is less important than toxicity, or vice versa, right? Where we are allowing differences. And that's what I think value systems are. They are always different, and we should, if we don't have no information about them, we should include them all. So I would say that it is a way to achieve neutrality in this respect.
Okay, thank you so much, Valentina. We've reached the end of our hour. I do have a couple of outstanding questions, and I would encourage our listening audience to send you an email directly to valentina@earthshiftglobal.com, and also to tune in next month as we will be applying this anticipatory approach to LCA with our CEO, Lisa Lauren, and we look forward to hearing more from that. So I would thank you all, and Valentina in particular, and I will end this webinar now.
Thank
Bye-bye.
you. Thank you, Holly. Thank you,
Thank
everyone.
you.
Bye.
Bye-bye.